Hello, and welcome to our video presentation. This project is funded by the Water Efficiency Technical Assistance Program and developed by our team at the Center for Irrigation Technology and McMullin Area GSA through the Grower Irrigation Academy. This video has been prepared for MAGSA landowners and explores how various soil water parameters affect irrigation practices to help improve irrigation water usage and efficiency. It's the first of 7 videos in this series. Please stay tuned at the end to find out about the other videos available as we dive into practical tips and expert insights to help make your irrigation more efficient and effective. Plants get their water from the soil, as we all know. The soil serves as a reservoir to store rainfall and irrigation water, releasing it gradually to plant roots. Therefore, understanding the soil reservoir and how it releases water is essential for farm irrigation water management. Soil-water relations directly impact water use efficiency, plant health, and crop yield. As you can see in this animation, the soil must have a reasonable infiltration rate for water to penetrate the surface layer and percolate to the deeper soil layers of the root zone due to gravity and capillary forces. Soil texture, structure, and organic matter primarily determine the water storage capacity, how easily water and air can flow through the soil, and how easily plants can take up water. Now, let us look at the soil composition and some basic soil concepts. Soil is a 3-phase system with 3 components: solid materials, water, and air. The solid materials are mostly soil particles or minerals, sand, silt, and clay, and a small percentage of organic matter. Healthy soil could have about 50% solids and 50% pores or voids filled with water and air. The soil is at saturation when all the pores are filled with water. Water drains from the saturated soils, and when drainage ceases or becomes negligible, the soil is at field capacity, the maximum amount of water a soil can hold against gravity. When plants explore all the available soil water, the soil is at the permanent wilting point. At this point, the soil is not completely dry and has some water, but plants cannot use the water effectively. An oven-dried soil has no water. The percentages of water and air in the soil vary throughout the irrigation cycles. Soil requires a balanced mix of water and air around the plant roots to promote optimal growth. Excess water can lead to root oxygen deficiency, impeding their ability to absorb nutrients. Conversely, insufficient water can stress the crops, reducing their growth and yield. An effective irrigation scheduling program is essential to maintain this balance. By accurately timing the application and measuring the volume of water applied, the scheduling program ensures that plants receive the right amount of moisture without over or under watering. The soil particles determine its texture, influencing the soil's ability to retain, transmit, and release water to the plant roots. Sands are the largest soil particles, silt is smaller, and clay is so tiny that it cannot be seen with the naked eye. Sandy soils have larger pore sizes, drain faster, and retain less water than loamy soils with more silt and clay. Clay soils have small pore sizes, drain slowly, and retain more water than sandy soils. Another factor is soil structure, which refers to the arrangement of soil particles into aggregates. Good soil structure with stable aggregates promotes soil water retention. Another important factor is organic matter content, which significantly influences water holding capacity by improving soil structure, contributing to the formation of soil aggregates, and increasing the amount of pore space within the soil. While you cannot fundamentally change your farm's soil texture and structure, you can improve them by adding organic matter to increase the water holding capacity. Compaction is another factor that reduces soil water storage capacity by decreasing soil pore space and altering soil structure. Compaction also reduces the infiltration rate, internal drainage, and root penetration. Now, let us look at the MAGSA soil map. The Academy has prepared a soil map for the MAGSA service area. Most of the MAGSA area soils are sandy loam or fine sandy loam with a high percentage of sand and a low percentage of organic matter. As you can see in this color-coded soil map, each farm typically has more than one soil type. Do you know how many soil types your farm has? It is easy to find out. Go to the Academy website and follow the link for the soil map as shown in the following video. To view the soil map, visit the MAGSA website at mcmullinarea.org/GIA, as shown here. Then, click on the soil map image to access the map. Use your mouse or the map zoom buttons to zoom in and out to locate and select your farm. When you click on any part of your farm, you see all the soil types present on your farm. The first 2 or 3 letters of each soil type represent the map unit symbol, and the rest is the map unit name. Write down the map unit symbols of your farm or copy and paste the symbols and names for your records. Additionally, click the arrow at the bottom or top of the small window, as displayed here. You can access further details about the soil type, such as the inches of available water storage at various depths. Please note that this additional information applies only to the selected soil type. To obtain information about other soil types, click on each color-coded area on your farm. The soil map provides information about the soil types across your farm and related data to help you improve your irrigation and nutrient management. For comprehensive data on your soil, utilize the Academy Soil Database. Access the database by clicking the link shown here. Select your soil types once the database is opened by marking the desired soil map unit symbols. To unselect any map unit, click on it again. After selecting all your soil types, click the Submit button. The table beneath the legend displays your filtered farm soil types. The first 2 columns list the soil mapping units and names, and all the necessary physical and chemical properties for irrigation and nutrient management are detailed in the subsequent columns by the soil depth. The descriptions of the columns are given in the table below. You can download the soil database for future reference. As you saw in the soil map, farms have unique soil types and textures, which determine how much water the soil can hold and release. You cannot fundamentally change your soil type's natural texture and structure. However, by adding organic matter, cover crops, mulching, and applying conservation tillage practices, you can improve the structure, physical properties, and soil-water relations of your soil. To learn about conservation practices suitable for your farm to improve soil quality, visit the Academy website to see local resources such as NRCS soil specialists and UC farm advisors for technical assistance. The following slide discusses the important soil parameters for irrigation management. Let us see the parameters involved in soil-water interactions. You might have heard at least 10 soil parameters listed here: infiltration, percolation, texture, structure, bulk density, porosity, saturation, field capacity, permanent wilting point, and available water capacity or plant available water. You can pause the video and take a moment to review these simple definitions. The essential soil parameters for day-to-day irrigation operations are saturation, field capacity, permanent wilting point, and plant available water. Before discussing these parameters, let us examine 2 other crucial soil-water parameters influenced by your farming practices. The first parameter is bulk density, which is the weight of dry soil in a given volume, typically expressed as grams per cc. Bulk density affects key soil processes such as infiltration, rooting depth and growth, available water capacity, soil porosity, and the availability of nutrients for plant use. Bulk density is mainly a function of soil texture. Sandy soils have lower pore space and a higher bulk density than silty or clayey soils. Bulk density also depends on soil organic matter. As the proportion of organic matter in the soil increases, the overall density of the soil mixture decreases. Bulk density also increases with soil compaction. These jars have equal soil weight, water content, and volume, thus identical bulk density. Let us compact one of the jars. However, in the real world, compaction is caused by heavy machinery, repeated machinery traffic, tillage practices, particularly when the soil is wet, and the lack of soil organic matter. The compacted jar has higher bulk density because of the reduced soil volume. Let us pour equal water on these soils. As we all know, compacted soil is undesirable as it restricts root growth and soil hydraulic properties. Bulk density is typically measured using a ring or cylinder known as the core method or cylinder method. The method involves driving a cylindrical volume into the soil at a known depth and then excavating and trimming the soil volume. The soil sample is then dried and weighed. The bulk density is calculated by dividing the dry mass of the soil by the volume of the cylinder. Your local soil laboratory can take soil core samples from your farm to measure the bulk density. The other soil parameter is porosity, which is the percentage of the soil's volume occupied by pores or voids. As mentioned earlier, the pore space can be filled with water or air, and porosity is a critical indicator of the soil's ability to hold and transmit air and water. Porosity is inversely related to bulk density. The higher the bulk density, the lower the porosity, which is the volume of soil pores divided by the total soil volume. However, porosity gives the percentage of pores and does not specify the size of the pores or whether the pores are filled with water or air. Measuring porosity is challenging under field conditions and is generally calculated using bulk density. Okay, now, let us discuss field capacity, permanent wilting point, and available water holding capacity. Soils have different field capacities and wilting points. This table shows the average and ranges of the field capacity, permanent wilting point, and available water for different soils. As mentioned earlier, the available water is the difference between the two limits, field capacity and wilting point. This table shows that fine soils like clay have much larger field capacities and wilting points than moderately coarse soils like sandy loam and thus can hold a larger volume of water because of the larger porosity. Sponges are similar to soil and have solid materials and pores. We use them here to visualize saturation, field capacity, and permanent wilting point. We have two slightly different sponges representing two different soil types. These sponges are dry. Let us start the irrigation. In the real world, irrigation takes many hours to complete, but for this video, we speed up the irrigation application. All the pores are initially filled with air, and water replaces the air as irrigation continues. When all the pores are filled with water, the soil is saturated and can no longer hold the water, and water starts draining from the bottom of the soil's root zone or sponges in this demonstration. Any water coming into the soil is drained out. Note that saturation happened first in the sponge with a coarse texture, which has larger pore sizes that drain faster and have a smaller total pore volume. Let us stop the irrigation now. When we stop the irrigation, the water keeps draining for a while. Under field conditions, the draining after full saturation could take 1 to 3 days, depending on the soil type. Sandy soils drain faster in about 1 day, while clay soils could keep draining for up to 3 days. When draining stops or becomes negligible, the soil is at field capacity, which is considered the upper limit of soil water storage. It should be mentioned that while field capacity is a useful benchmark for irrigation management and understanding soil-water-plant relationships, it is not an absolute constant and could vary by soil type across the farm. Plants use the soil water gradually depending on the evaporative demands. Let us assume that plants have removed all the available soil water by squeezing the sponges. The soil is at the wilting point now since plants can no longer effectively take up the water. The wilting point is the lower limit of available water, but this is just a cutoff point, and plants begin to stress well before the wilting point. The available water holding capacity is the amount of soil moisture available to plants between field capacity and the permanent wilting point we just squeezed out. The soil still has some water at the wilting point as these sponges are not completely dry, but they are held tightly by the soil particles, and roots cannot withdraw the remaining water effectively. You can see that the sponge with the smaller pore size could store more water than the sponge with the large pores. Do you know how much water your soil can hold? To learn, visit the Academy's soil database and look for the volumetric water content at field capacity, permanent wilting point, and saturation percentage. As shown in the table on the screen, soil water is expressed as volumetric water content and inches of water per foot of soil. The following slides show how soil water can be measured and expressed in several terms. Soil water can be expressed by water content or potential. Let us talk about soil water content first. The soil water content can be expressed by weight, volume, or depth. Gravimetric water content is the mass of water divided by the mass of the solid. To measure it, you take a soil sample and weigh it when it is moist. Then, oven dry it and weigh it again. The weight difference is the water's weight. If you divide the water's weight by the soil's dry weight, you get the gravimetric water content. This fraction is often shown as gram per gram in soil labs, but it is usually converted into a percentage by multiplying by 100. The gravimetric water content is relatively easy to measure but not useful for farm irrigation management. The other unit of soil water content is the more familiar volumetric water content, which is more useful in managing irrigation. The volumetric water content is the volume of water over a known soil volume. It is essentially the portion of the total soil volume that is made up of water. The volumetric water content is difficult, destructive, and time-consuming to measure directly in the field since it requires sampling a known soil volume. It can be calculated by multiplying the gravimetric water content by the soil bulk density. The volumetric water content is commonly indirectly measured by various soil moisture sensors, which will be discussed in video number 2 of the Academy video series. The gravimetric and volumetric water contents show how much water is in the soil per unit mass or volume. When we talk about how much water there is in a field, it's often easier to use equivalent depths of water instead of just talking about the amount of water. Imagine you have a soil profile to a certain depth, and this profile has a certain amount of water stored in it. The equivalent depth of water refers to the depth of water covering the soil profile if all the water stored in it was spread evenly across the surface. It shows how many inches of water are in a specific vertical soil depth. The water depth calculation is commonly based on the volumetric water content. For example, if the volumetric water content in the first foot of soil is 16.5%, the 16.5% can be expressed as a fraction or 0.165 inches per inch. We can calculate the water depth in the first foot, or 12 inches, by multiplying 0.165 inches per inch by 12 inches, or 1.98 inches. Soil water can also be measured and expressed as water potential. Water potential quantifies the energy state of water in the soil compared to pure water at the soil surface, which has zero potential. When water enters the soil, water molecules bind to the soil particles, causing their energy state to become negative, and plants must spend energy to take up the water. Water potential is also called water tension and soil suction. As water in the soil decreases, the water molecules bind more tightly to the soil particles, making it more difficult for plant roots to take up the water. Soil water potential indicates how easily or difficult plants can absorb water from the soil. For all practical purposes, soil water can be classified into 3 categories. The first category is gravitational water in saturated soil. The second category is loosely held water between field capacity and permanent wilting point, which is plant available water. The third category is the tightly held water that is unavailable to plants. The standard units for water potential are megapascals, kilopascals, bars, and centibars. The head in feet of water is given as a reference here. In many soils, the soil water potential at field capacity is about -10 to 33 kilopascals, or -0.1 of a bar to 1/3 of a bar. Sandy soils have lower tension than clay soils at the field capacity. The soil water potential at the permanent wilting point is -1,500 kilopascals, or -15 bars. However, these values are not exact and can vary for different soils and crops. Water flows from high potential to low potential areas in the soil water plant atmosphere systems. Plant roots must have a lower water potential to overcome the soil water potential and extract water from the soil particles. Then, water moves through the plant along a gradient of water potential and reaches the leaves, evaporating into the atmosphere. Note that the air water potential is much lower than the plant water potential when water changes from liquid to vapor as it exits the leaves and is lost to the atmosphere. The soil and plant water potentials in this image are just examples, and these values depend on the soil and plant water conditions and evaporative demands. Irrigation scheduling determines how much and when to apply water. The irrigation timing and volume depend on the soil characteristics and effective rooting depth, which will be discussed in this slide. The main soil parameters for irrigation scheduling are field capacity and permanent wilting point. As mentioned earlier, the water held in the soil between field capacity and the permanent wilting point is referred to as available water capacity or plant available water. However, not all the available water in this range is readily available for plant use, and plants experience water stress well above the wilting point. Therefore, farm management must decide on the soil water depletion level between the field capacity and the permanent wilting point to avoid crop water stress. This level is called Management Allowed Depletion or MAD, which refers to the percentage of available water capacity that can be depleted from the soil before irrigation is needed. Farm management determines the MAD. The management allowed depletion level depends on crops, soil types, and weather conditions, typically about 50% for most crops on average. However, it may be higher in some tolerant crops and lower than 50% in sensitive vegetable crops. The MAD level could also vary for the same crop during the growing season, depending on the sensitivity to water stress at various stages of crop growth and development. Therefore, deciding on the MAD level to schedule irrigation during the growing season is critical. Consult your UC farm advisors regarding the MAD levels for your crops. Video number 5 of the Academy series will also discuss general MAD values for different crops. The sketch on the screen shows that management allowed depletion is a concept in irrigation scheduling that determines how much to irrigate. MAD is a threshold level that refers to the portion of soil moisture that can be depleted before irrigation becomes necessary to prevent crop stress. The threshold is also known as the refill point. As shown on the screen, the volumetric soil moisture content at the refill point for this example, an assumed MAD of 50%, is 16.5%. Note that the difference between the field capacity and refill point is only 6.5%. This narrow range means that the soil in this example can only hold less than 7% of its volume between the field capacity and the refill point for irrigation management. Such a narrow range underscores the need for careful irrigation scheduling and dedicated soil water monitoring. As shown in the example, to calculate the net irrigation or how much to apply, you must measure or estimate your soil's field capacity and permanent wilting point, decide on the MAD level, and the managed rooting depth. As mentioned in the previous slide, to see the USDA-based soil data, visit the Academy's website, find the soil database, have your soil mapping units handy, and see your farm's field capacity and permanent wilting point values for your initial estimates. Returning to the example on the screen, the total available water is calculated by multiplying the available water capacity and rooting depth, 2.34 inches, in this example. The depth of the readily available water is calculated by multiplying the total available water and the MAD level, which is the net irrigation application, or 1.17 inches. The gross irrigation application is obtained by dividing the net amount by the distribution uniformity of your irrigation system. Video number 4 of the Academy's series will discuss distribution uniformity and how to improve it. The effective rooting depth is usually less than the maximum rooting depth because the rooting density decreases with depth, and most of the plant's feeder roots are contained in the upper part of the rooting depth. The managed rooting depth for irrigation scheduling refers to the depth when applying irrigation to refill the soil profile based on the effective rooting depth. Selecting a managed rooting depth simplifies water and nutrient applications and management. Since the managed rooting depth is less than the maximum rooting depth crops can explore, it also serves as a safety margin. In the previous slides, we have primarily focused on soil water. In the next slide, we will briefly discuss irrigation water quality for micro-irrigation. According to the MAGSA Groundwater Sustainability Plan, groundwater quality in MAGSA is generally well suited for irrigation and domestic use, although groundwater issues may exist in localized areas within the agency, including chloride, nitrate, and salinity. Irrigation water quality is vital for two main reasons: salinity and the clogging of micro-irrigation equipment. Soils and all irrigation water contain salts. Plants selectively take up certain minerals, leaving most salts applied with irrigation water behind. Over time, the salt content of soils may increase, reaching levels that cause crop yields to decrease below their potential. In such cases, the soil is said to be salt-affected, and leaching is needed. However, the critical salt levels vary with crop types. Plugging of emitters is the primary water quality concern for micro-irrigation, resulting in low system distribution uniformity. Plugging can occur due to physical, biological, and chemical reasons. Emitters may become blocked due to small particles passing through the filter or small particles clumping together and forming a larger mass. Bacteria and algae can grow in the micro-irrigation system, resulting in slime buildup. Some minerals like iron, calcium, magnesium, and manganese can precipitate in micro-irrigation systems. Typical management strategies to avoid clogging include using filters to block mineral and organic particles from entering the irrigation system and chemical injections to prevent mineral precipitation and slime development. Maintaining uniform distribution is critical for achieving high irrigation efficiency, and poor system maintenance is the leading cause of low distribution uniformity. Video number 4 in the Academy's video series has been prepared to address the maintenance of irrigation systems. We have reached the end of our technical presentation. Before saying goodbye, let us briefly discuss the project in the next slide. The Water Efficiency Technical Assistance Program of the California Department of Food and Agriculture has provided the project funding for improving water use efficiency and nutrient management for the McMullin Area Groundwater Sustainability Agency, or MAGSA for short. The Center for Irrigation Technology at the California State University at Fresno, jointly with MAGSA, established the Grower Irrigation Academy, prepared the learning and training materials for this project, and performed outreach activities. As required by the funding agency, the learning and training materials are prioritized for socially disadvantaged farmers or ranchers of the MAGSA service area located around Kerman in Fresno County, California. This project aims to help MAGSA growers improve irrigation water management, ensuring that crops receive the necessary moisture at the right time while minimizing water waste and conserving and protecting the available resources. Several workshops, webinars, field days, and other diverse and innovative outreach activities through MAGSA communication channels and social media have been planned for this project to share ideas and experiences and discuss challenges and solutions. Additionally, the Academy prepared 7 videos to provide educational and learning materials for growers and landowners in the MAGSA service area to improve irrigation management. This is our first video, covering the basics of soil water for irrigation water application and scheduling. The second video covers sensors and devices that measure and monitor soil water for irrigation application and scheduling. The third video presents the basics of deficit irrigation practices, which is particularly important for this groundwater sustainability agency. The MAGSA has limited irrigation water supplies, and deficit irrigation scheduling can help the landowners and the agency better manage the limited water supplies. The fourth video helps farmers and ranchers maintain their irrigation system to improve efficiency and distribution uniformity to conserve irrigation water supplies. The fifth video provides learning materials to schedule irrigation using improved soil-based and weather-based methods. The sixth video discusses nutrient management to maximize crop yield and minimize nutrient waste and leaching to groundwater water supplies. And the last video shows the importance of record keeping and provides simple bookkeeping techniques to manage farm irrigation data to track the farm records. We have reached the end of this video on the basics of soil water. Thank you for watching. We hope you found this video helpful and invite you to explore our other video series on the Academy website when posted.